Okay, so the last set of rules we're going to talk about is going to involve naming acids. So first, a little bit of information about acids. For this initial definition, we're going to say acids are going to be able to donate H plus ions when added to water. Once we get into talking about acids more, we'll see some slight differentiations between those, but for right now, an acid is something that's going to give up H plus ions. Typically, they're going to have a sour taste. Now, when I say that, though, that's really for dilute concentration of these. You don't want to be tasting concentrated acids because they're very corrosive and they'll actually do damage to you. Typically, when we talk about these acids and the things you're tasting, they're going to be lower pHs, they're going to be weaker acids, lower concentrations, that sort of stuff. One of the most common ones is citric acid, the citric fruit, things that give that fruit its bite, its sour taste, like a lemon. When you look at those really sour candies, those have higher concentrations and different types of acids in them. That's what's giving it the sour taste, though. So now if we go to certain types of acids that are stronger acids and at higher concentrations, those acids can actually dissolve metals. Once again, that's why we don't want to be tasting concentrated versions, because if they can dissolve metals, they'll definitely be able to dissolve your taste buds. So when we're looking at acids and we're looking at the formulas of those acids, they're going to be really similar to ionic compounds, except the cation is going to be limited to H+. So that actually makes our life a little bit easier, so we don't have to worry about all those different types of cations that we had to with ionic compounds. So let's look at an example of these formulas. If I want to form an acid from the sulfate ion, that sulfate has a -2 charge, okay, which means it has extra electrons. Well, in this case, what's the source of those electrons going to be? Well, each hydrogen atom can lose an electron to form the cation H+. So for every hydrogen atom we have going to H+, we gain 1 electron. Those electrons then are going to that sulfate ion to give it that -2 charge. So that's where we form that anion, the SO4 2-. All right, so keep in mind, those electrons lost must equal electrons gained, so those charges must be balanced. All right, we need a net overall charge of 0. So if we start with our two ions, H+ and SO4 2-, H+ is a +1, SO4 is a -2, add them together, I end up with a -1. I haven't reached that charge of 0. But what I do end up with is HSO4 1-. Now, because I have that hydrogen attached to that sulfate ion, technically this is still an acid, okay, because it can give up that H+, which is by definition an acid. However, for naming purposes, because it still has a charge, we're still going to treat it as a polyatomic ion for naming. So for that particular polyatomic ion, that's the hydrogen sulfate ion or the bisulfate ion. Okay, so let's get to actually forming the formula then for the acid form. Balance out the charges, I need to add another H+. Pretty straightforward, so I end up with +2 plus a -2 is going to be equal to 0. So my formula for the acid would be H2SO4. Overall charge is 0, the cations are going to be H+. Because of that, acid naming rules are now going to apply. Okay, so if we have an overall charge of 0, and our cation is an H+ ions, we're dealing with an acid. We're not dealing with an ionic compound. Now, when naming acids, we're going to worry about two different types. We're going to worry about binary acids, which are acids formed from monatomic anions. Right? So binary, once again, means it only contains 2 elements. So an example of this, if I take the chloride ion, Cl-, and go to its acid form, HCl, I added an H+ to balance out that minus charge, that's a binary acid. Okay, we're only dealing with monoatomic anions. The other type is going to be something called oxyacids. Those are going to be formed from oxyanions, polyatomic ions that contained oxygen. So an example of this, if I look at nitrate, that's an oxyanion. It's a polyatomic that contains oxygens. Its formula is NO3 -1. So to write the acid form of that, I'd add just an H+, so it'd just be HNO3. Right? HNO3 is a type of oxyacid. Okay, so let's start with the binary acids. Now, keep in mind we need to be dealing with monoatomic anions, so if you remember back to the table from when we were talking about naming ionic compounds, still going to keep the same type of anions. When we go to name these binary acids, the way we're going to name them is we're going to start with hydro. We're then going to use the base name of the nonmetal plus an IC. And then we're going to add the word acid at the end of it. So HF, it's binary Y, just 2 elements. F is a monoatomic anion. So first, we're going to start with the hydro. Right? The base name of the nonmetal, F, is going to be fluor. F stands for fluorine. We drop that INE ending. Gives us that base name. We're going to add ic to that. And then we're going to add the word acid. So put it all together. HF is hydrofluoric acid. Key thing to remember with fluorine, it's not flour, F-L-O-U-R. It's fluor, F-L-U-O-R. That's a common mistype that people put with fluorine. They spell it F-L-O-U-R. Okay, so make sure you get the name of fluorine down because that's an easy mistake to make. All right, let's look at another version of a binary acid. So HCl, we have hydro, base name is chlor, add the ic, acid, hydrochloric acid. All right, so naming binary acids from formulas. Binary acids are relatively simple as long as you got those monatomic ions down. Okay, it's pretty straightforward. All right, let's look at getting the formula from the name now. So if I start with hydrosulfuric acid, I need to get back to the formula. So with hydrosulfuric acid, well, first I'm going to remove acid from the name. Okay, I've added the ic, so I need to remove the ic from the name. I need to remove the hydro from the name. When I do that, what I'm left with is my base name, which is what I want to pull out of there, which is sulfur. Okay, well, when I look at that base name, that helps me determine what monoatomic anion I'm dealing with. Once I know the monoatomic anion, I just need to add enough H pluses to balance out the charge so I get a charge of 0. So when looking at this, sulfur is going to be an S2 minus. I need 2 hydrogens to balance out the charge, so I have a +2 plus a -2. Gives me an overall charge of 0. So my formula is H2S. So the binary acids are relatively simple, just like the naming with the monoatomic ions and ionic compounds was relatively simple. Now we get into the trickier part. It's not too bad though, as long as you know those polyatomic ions and you know the rules of ionic compound naming, because we're going to use those similar rules. Right? We're just going to make some slight changes to those. Okay, so when we're naming oxyacids, remember oxyacids are going to be dealing with polyatomic ions that have oxygens in them. So we're going to take these polyatomic ions, add enough H pluses to get a charge of 0, that will give us the acid forms of this. Remember from the ionic compound naming rules, I'm going to go through it again because it's so important. Remember, you need to know at least the 8 forms of these, so the name and the formula and its charge. Once you know the 8 forms, you can figure out whether you're dealing with an 8, an ite, a perate, a perite. Okay, we went through those rules. So chlorate was ClO3 minus 1. If I know that form, if I subtract an oxygen, I go to chlorite, ClO2 minus 1. So 8 to ite means I've lost 1 oxygen from my 8 form. If I go to the perate form, I've added 1 oxygen. And if I go to the hypoite form, I've lost 2 oxygens from my 8 form. Okay, you need to know those rules. We need to know those polyatomic ions when we're going to look at naming oxyacids. All right, so with those polyatomic anions, or oxyanions, are the ones we're going to worry about. When naming those in acid form, if you have an ATE ending to your oxyanion, you're going to use this rule to name your acid. You're going to take the base name of the oxyanion, add IC, and then add acid. You've got the name. So if I look at HNO3, if I look at the oxyanion involved here, I take my H pluses off. I've got NO3 minus 1. That's the nitrate ion. I have an ATE ending. I'm going to drop that ATE ending, so I'm left with NITR. NITR plus ic plus acid, so the name of this is nitric acid. So I drop my 8 forms and add an IC if I have an acid involving an oxyanion that has an 8 ending. All right, let's look at another example of this. H2SO4. I take all my hydrogens away. I get the sulfate ion. With the sulfate ion, drop the 8 ending. Now, when I drop that 8 ending, I actually need to go back to the base name. The base name for the sulfate was actually sulfur. And there'll be some tricks like that that you need to get used to, but you'll get that with more practice. Okay, But drop the 8, go to the base name, add IC, add the word acid, and I end up with the name of sulfuric acid. Now, this is sulfuric acid. Don't confuse that with hydrosulfuric acid. Hydrosulfuric acid is a binary acid, not an oxyacid like sulfuric acid. So if you notice a difference between these two, I have H2SO4 as sulfuric acid, H2S is hydrosulfuric acid. That hydro means I'm dealing with the monoatomic ion. Okay, when I just have the ic ending, that means I'm dealing with the 8 form of the oxyanion. So don't get those confused. Okay, so the other type of ending we have with these oxyanions is the ITE ending. If we have something that has an ITE ending, we're going to use the base name and add an OUS, HNO2. What's my anion here? NO2 minus 1, that's the nitrite ion. Nitrate, NO3 minus 1, lose 1 oxygen, I go to the ite form. So the NO2 minus 1 is the nitrite ion. I'm going to drop the ITE ending, go to my base name of NITR, add an OUS, add my acid. So the name of this would be nitrous acid. And don't forget to include those acids in all of these too, because it's important. It's part of the name is to tack on that acid at the end. All right, so let's look at another example of this. H3PO3, that's the phosphite ion, PO3 2 minus. Going to drop the ite and go back to the base name. Well, the base name actually is phosphor. I'm going to add an OUS, going to add the acid, and I'm going to end up with phosphorus acid. So we've talked about getting the names from the formulas. Now let's talk about getting the formulas from the names. Let's look at hypochlorous acid. What I need to look at is the ending there. It's the OUS. That tells me something. It tells me that if I'm using OUS, that means I'm using an oxyanion that should have an ite ending to it. So remember, I added an OUS to anything that had an ite ending. So when I work this backwards, I drop the acid, drop the OUS, I'd end up with hypochlor, add the ITE to it, so I get hypochlorite ion. The hypochlorite ion is ClO1 minus. So I've got ClO1 minus. I needed to add enough H pluses to balance the charge. Well, I only need one H plus. So that gives me a formula of HClO. Be careful of this. This causes some confusion. Notice it's hypochlorous, not hydro. Hydrochloric acid with the IC and the hydro, that means we're dealing with monoatomic. With hypo, it's just a form of that oxyanion. Okay, it's the OUS we want to focus on. We're dropping the OUS, getting the ITE ending. Okay, so be careful of confusing the hypo and the hydro. Okay, so let's look at another example of getting the formula from the name. If I have perchloric acid, well, I look at that IC ending. I don't have a hydro out in front. I've just got the IC ending, which tells me I'm going to be dealing with an 8 form of my oxyanion. So I remove the acid, remove the ic, end up with perchlor. Take that perchlor and add the 8 ending to get perchlorate. If I know perchlorate is ClO4 1 minus, to balance out the charge with H pluses. So I end up with a formula of HClO4. Alright, so when looking at these formulas and names of acids, you need to be able to take the names, write the formulas. You need to be able to take the formulas and write the names. The main thing to consider is if you have a monoatomic anion, has an IDE ending, you add enough H pluses to balance out its charge, and it becomes hydro and ic as far as the acid name goes. If you have something that has an ATE ending, it's an oxyanion, you add enough H pluses to balance out the charge, and that goes from 8 to ic. You then can go from ite to OUS. So I really try to remember ide goes to hydroic, 8 goes to ic, ite goes to OUS. Keep in mind though, you need to go backwards too. Hydroic goes back to ide, ic goes back to 8, OUS, us, goes back to ite. You've got to learn these naming rules for these acids. Right? Here's another little example of a flow chart that may help you out if you want to look at it. All right, let's go through a couple more of these. So what I want you to do is give the formula and the name for the acids that would be formed from the following anion. So if I said I wanted you to form the acid from the bromide ion, well, you'd have to be able to recognize that bromide, the IDE ending, monoatomic, so I'd be dealing with Br minus. If I have Br minus, I'd add just a single H to balance out its charge. Because I have the IDE ending, I'd use the hydroic, so I'd have HBr and it would be hydrobromic acid. If I have the acetate ion has an ATE ending. It's a polyatomic ion, it's an oxyanion. So when I drop the ATE, I add IC. So I go from acetate to acetic acid. Acetate ion is C2H3O2 minus, so I only need one H plus to balance its charge. If I look at sulfite, ITE ending, need to know what sulfite looks like. So sulfite would be SO3 2 minus. I'd need two hydrogens to balance out its charge. I'd go from the ITE ending to the OUS ending, so I'd end up with sulfurous acid. You need to be able to convert between these formulas and names. Okay, we're going to go through a couple more, see if you can get them. Phosphoric acid, what would that be? Well, I've got an ic ending, so I'd have the 8, so phosphate would be the ion, so I'd end up with H3PO4 for the formula. If I have H2CrO4, well, CrO4 is chromate, so 8 goes to ic, so I'd end up with chromic acid. If I have iodous acid, I've got that OUS ending. OUS comes from the ite form of the polyatomic ion. So with iodous acid, I'd end up with HiO2. What about Hi? Well, that's a monoatomic anion, so I'd end up with hydroiodic acid. What about dichromic acid? Well, I have the IC ending, so I'd drop the IC, put the 8 on, so I'd be dealing with the dichromate. So my formula would be H2Cr2O7. Alright, what about H2PO41 minus? Well, for this one, it still has a charge. Even though we've added H pluses, it still has a charge, so we can't use acid naming rules of this because of that charge. So this is still a polyatomic ion, so its name would be the dihydrogen phosphate ion. So always make sure you're paying attention to what you're looking at. Once again, you're dealing with a covalent compound, which is a nonmetal and a nonmetal combined together. Are you dealing with an ionic compound, which involves a metal with a nonmetal? Or are you dealing with an acid, which involves H pluses with either a nonmetal or those polyatomic ions? Depending upon what you're dealing with determines which set of rules you use. And you need to know all of those rules. Alright, that's going to be it for the acid naming rules.